Okay, welcome back to LearnPiezo.org, and we're continuing our lecture series or project series on ultrasonic cleaning. Sort of more do-it-yourself than you might find for instructions already on the internet. And today I have an ultrasonic cleaning transducer, and we want to start learning a little more about what component we have. And the first sort of step in all of this, well, one of them, is finding the resonance frequency. We're going to do a couple things, not today, but today we're going to find the resonance frequency. Later we're going to find the capacitance, and we're also probably going to find the resonance impedance, and try even for the anti-resonance impedance in that frequency as well. I'm sure you've been watching all the other videos and you know very well what these mean. But today we're just going to find the resonance frequency, a very simple experiment. So here's the experimental setup, and all these different components are listed on my website, and please use those links to help support LearnPiezo.org. So I'm going to actually describe this whole experimental setup. There's another detailed picture in the next slide, so I'll go over that as well. And again, all of this will be uploaded on my website, LearnPiezo.org. I'm sure you saw we have the website outlined right here. So what exactly is going on here? This is a USB oscilloscope, a PicoScope, the 2000 series. So that's the scope. Then we have two different cables here. The first is a voltage probe. Okay. The other one is a sort of alligator BNC. So I'll explain now how the circuit is set up, and I'll explain it in this slide here, in another slide. So we have our power source, because you're always going to need a power source, and that is hooked to ground. Actually, I'm powering off my laptop, so there's actually no ground. It's just relative, which is sort of the neat thing about having a USB oscilloscope, is that you can do floating measurements. But your common ground has to be the same. So we have that wire coming out from the generator, and remember the generator in the schematic shown here, it is actually here. So this is the generator. That cable is then going to the ultrasonic transducer. So the ultrasonic transducer, in case you didn't see it properly, it looks something like this. So this part is metal, this part right here is metal, and these two things in here are ceramics, piezoelectric ceramics. And there's like a tab sticking out. So I can't use black, obviously. So we have these tabs sticking out, which are going to be used to provide the electric driving, and they're polarized in opposite directions. And I'm not going to talk about that just yet, because we're going to actually have another lecture just talking about how this piezo is set up. But just understand that you hook these cables up, and you then get vibration, and you get your ultrasonic whatever. Just remember to put that red cable to the middle one. The red goes to the middle. I'll explain that sometime in the coming parts. These are going to be fairly short and easy lectures, so I'll just cover the information when we get to it. It won't be too long. So then in this part you hook this part is the other. It goes to the circuit. So we're going to have this middle section. It's going to be here. So we're going to have this. I'll draw a mini little piezoelectric. I'll just draw that in red. Then we have these are two layers in the middle. And if you see the picture, this is what it looks like. See? We have the metal on top, metal on bottom, and the two piezos, and we have these electrical leads sticking out where we're going to actually make the connection. So then we have the piece of metal on the bottom, and we have one sticking out here, one sticking out there. So the one in the middle, we should connect that with the wire. And then we go and we have a resistor. In this case, I just had a 325 ohm resistor laying around, so we're just going to use 325 ohm, and we're going to hook that to ground. So this is the red part of that alligator clip that goes from here. That red part is going to go here, and then this is a twisty tie, which I just cut the ends off, both of them exposing the metal wire underneath, and I just use the breadboard to hook this resistor up to that twisty tie. And the ground is then achieved using the black alligator, which is coming from this BNC cable. The voltage probe is going to be hooked here. We're going to get that voltage probe, that long looking little, and it has a little hook at the end, so we're going to hook the end, and then we're just going to measure the voltage from there. And you have to put the voltage probe's ground, because the voltage probe also has a ground alligator clip. You have to hook that to the black one. So all the black alligator clips are all hooked up to the end of the resistor. Now we're able to rotate, or not rotate, now we're able to flow current because we have a complete circuit. Otherwise there'd be trouble and we wouldn't get any signal. So here's what it looks like close up. We have our red alligator clip coming here, and that's black. It should be black. Let's try a different one. How about yellow? So we have this red. This charges the middle one, and then this then completes the circuit. These two metal portions are actually connected to this internal screw. So this electrode is sort of already connected to the bottom one, and you're charging the middle one, so you're generating field going outward in the piezoelectric ceramics which are there. And I'm going to explain a little bit more about that ultrasonic transducer, maybe even in the next video, because perhaps I should have done it before this. But anyways, you may have been already familiar with the transducer, so let's just keep going. So then that goes down to the breadboard, which connects to this 325 ohm. And this may be actually too large depending on what we're going to find for this transducer. I'm guessing for this transducer is going to be around a few hundred ohms for the resonance impedance, but it could be wrong. I think it's going to be about 20 kilohertz, 20 to 50 kilohertz. I forgot to look at the data sheet, but we have that. We're going to have that link for the product on Amazon on the website learnpiezo.org. So now we're actually going to get into the interesting part, and I'm going to show you this exact circuit is hooked up right now to the right of me. You can't see it, and didn't feel like merging two videos together and doing a horrible job taping things with my phone. So I just gave you those nice slides so you can take a look at them in the notes later. So now we're actually going to open PicoScope. It's the USB oscilloscope's built-in software. So I installed that already. The USB oscilloscope tends to do this clicking thing, so that is showing that it works, and it's like a red. So at this point I actually need to reduce the size of my window, because you will not be able to see, you need to see the top menu. There you go. So this is what you need to see. Right now, no signals on. So channel 1 is active, channel A, and that's, if you remember, that's where we had this. That is where the first probe was. So let's just move this back here to make it all simple and nice again, and move this down here. Okay. So the first thing we would like to do is put some voltage on it. And you click this, and you turn the signal on, and now there's signal. You're noticing that it's sort of weird, not really anything, it doesn't make any sense really, right? So right now, we're going to do a couple of things to make things easier to analyze. We're going to use a sine wave. We're also going to press this lightning button, which is an auto setup, which is, you may be familiar with that from a traditional oscilloscope, which sort of helps you find the signals. I'm going to increase the voltage, and there's no trigger right now, so we'll deal with that in a second. We want to increase the effective bits because now we're using a sine wave. We're not worried about losing spectral information. So it improves a little bit there. And we increase the voltage, only goes to 2 volts. Now everything seems to be connected properly. It will only go to 2 volts. That's the amplitude of the signal. So let's increase that frequency. Now I can sort of hear that going off. 6 hertz, 7, 8. I'm going to try to move to my microphone right next to the, well, it's sort of far away, I can't really get there, but we can increase this frequency, and you see this. What are you actually seeing here? This is the current in the piezo. Right now we're not generating much current at all, but we're also measuring quite fast. So this is a little better. See, we were sort of oversampling, so we need to get to the correct sampling rate, which is something which more or less like this. So we have to use a trigger in order so we can get that repeating signal effect. So here we go. So we have a repeating signal. We have to adjust this scale so it reads at the proper frequency. It takes the number of cycles because this is not a high performance oscilloscope like you may be used to using on a benchtop, which has like megahertz of bandwidth. This is just to give you an idea, sort of I don't remember the specs on this, but it's not a high performance oscilloscope. It's sort of like it's good for what it does though. So if you increase the signal, the time base here to the proper time base, which you could sort of inspect the signal visually, it'd make it easier for that. Then you'd have a good signal. You'd have a good ability to understand the wave, and you'd get a proper reading for its amplitude. So here we have 7 volts. So let's just calculate what's happening here. I'm going to make a measurement. The measurement I'm gonna make is we want to make a measurement for peak to peak, because right now we don't have the whole waveform, and in order just to avoid losing some information, so let's do peak to peak information, the whole trace. Okay, so we had the peak to peak value is 20.1 millivolts. And the amplitude here is also, it's 2, which would make it 4 volts peak to peak. Let's just open here. Okay, so here's an Excel sheet we're all used to using. So we're reading 20 millivolts. And I think I'm on the 10 times setting. Let's go back to the 1 time setting, actually. This is not correct. So it's not 20 millivolts. I was using, see, the probes have a 10 time setting, so if you want to measure higher voltages, you can measure it reduces the voltage by 10. It reduces the voltage by 10 times, so you can read higher voltages through the oscilloscope, because the oscilloscope only has a certain range of voltage limit. So you sort of limit the outside, so you can, and you can take that into account, so you can measure large voltages. But in this case, we're going to be measuring a small voltage. I changed my USB oscilloscope probe back to 1 times, which is proper amount. So now we have 180 millivolts. So the resistor value that I mentioned, the resistor that we are using is 325 ohms. The voltage we're reading is 180 peak to peak, which and since we are actually using peak to peak, this would be 4 volts peak to peak. 4, so voltage reading, voltage input, voltage input. So that's also peak to peak. So Ohm's law, right? V equals IR. So you divide the voltage by the resistance, and then you would get the current. So the current, and this is going to be also, I guess, a peak to peak if you use these values again. So equals. So voltage is 180 millivolts. So that you can divide that by 1,000, divided by the resistance, which is 25. So we have a pretty small voltage. Pretty small current we're reading here. Probably we're nowhere near resonance. You may be able to use this value to calculate the capacitance, although I would not do that right here. So if you reduce the value to about 3, and we should probably reduce that, we should actually be able to measure the capacitance. But we'll do that in another video because it's not the point of what I'm trying to do here. So here's 6, here's 7, here's 8. I can hear the transducer now, because 10 hertz is still audio. You can still touch it. This is so low. This voltage and this current is coming out of your laptop, so it's not gonna hurt you. So I'm expecting. Okay, see that we get that over voltage. So let's just reduce this, because when we get to the resonance frequency, we get a lot of motion, and we get a lot of motion, we then get a lot of current. So let's keep that in mind. This is using auto. I'm going to use plus or minus 100 just so I can get, I can see the difference. So let's keep continuing on. Okay, seems like we got, so this is a 65 millivolts. Alright, sorry, let's go back. So this is 65 millivolts peak to peak right here. This is the live value. And that is 120, so that's much closer to the resonance frequency. This is also pretty close to the resonance frequency. Channel over range. Let's just make it larger. So right now, what I'm trying to do is hunt for the resonance frequency. So 20 kilohertz makes it 122 millivolts, and 30 kilohertz makes it 170. 40 kilohertz makes it 256 peak to peak. And now that I have a larger signal, we will just do that 317 peak to peak, because you have to adjust it. And now we hit low. So we can say probably that the resonance frequency is somewhere in between 30 and 50 kilohertz, because that's where the maximum occurred, 40. But now we have to find where that is exactly. So that's 317, right? So let's go down to 35. Okay, that's the low. 38. Now this would always be a lot easier using a traditional scope, but the thing with the traditional scope, this is going to be a lot easier to program. And you're going to see that in the future. And this is 2 for 1. You get both the function generator and the measurement capability, the 2 voltage channels. So it's sort of a really good deal in that sense. So as long as you can amplify the signal to do something practical, then it's going to be quite useful. So we're at 40 kilohertz at 317. 42. Okay. 41. 40. So 317, 40. Sorry, this is a little bit monotonous. I didn't program it yet, so but you're basically going to understand what I'm going to do when I program. When I'm going to program this, I'm going to sweep the frequency and I'm trying to understand the voltage. So we know the resonance frequency is about 41 kilohertz for this. Sorry, about 40 kilohertz. I think that's what I remember correctly. That was the actual spec. So we found the resonance frequency, 40 kilohertz. Now we're going to do some math. There may be some reasons why this math is not going to be correct, and those have to do with the experiment, but we are not going to worry about that right now. We can then, so we have found the resonance frequency, by changing the frequency that we're driving the whole system, and we're finding at which frequency is the current the largest. And when we find the frequency which the current is the largest, that means the piezo is vibrating the most at that frequency, and thus we are able to locate that resonance frequency quite easily. So here we have 317, and then in future videos we're actually going to show how to program this oscilloscope to help you find an accurate measurement of the resonance frequency. So we have 320 millivolts peak to peak. So we have 320. The voltage input now is less. I don't think that the voltage input is now 1 volt peak to peak, because look, we have 500 millivolts, so that makes it 1 volt peak to peak. The resistor is still the same, doesn't change. So the current in peak to peak is going to be 1 amp. No, that's not correct. And the reason that's not correct is because this should be divided by 1,000. It's almost 1 milliamp. That's how much current is actually going through the system at this point. It's also due to the fact that probably the transducer has a lower voltage than, has lower impedance, so we're gonna have to use a different way. But this video is plainly just to show how to find the resonance frequency, and I'm sort of leading on to other things. I'm leading on to how I'm going to calculate the resonance impedance, which will be important for a practical piezoelectric device, because you need to design the driving system accordingly, according to those electrical characteristics, which change significantly. So in this lecture, if I would not mind to write, we learned how to use, basically how to set up the circuit, measure the resonance frequency, we'll call that FR. We learned about some of the connections, and the connections, that's sort of the same thing. And the third thing we can say we learned was how to find the resonance frequency. And we did that by varying the driving frequency. So I'll call it drive. We're varying the driving frequency, and we look for the largest current. And for all practical purposes, the current is proportional to the vibration of the piezoelectric. So when you drive the piezoelectric at its resonance frequency, it's going to vibrate the most, it's going to do the most stuff. And the whole point of these lectures is to understand how we can make piezos do stuff, and how we can be smart about it and make it do really cool stuff. So remember to visit learnpiezo.org, okay? And at learnpiezo.org, we're going to have a list of all these items with links to the ones that I have. Learnpiezo.org. So we're going to have a list of all the items, so check that out. Thank you. See you for the next part. So the next time we're going to calculate the capacitance. So that will be part C. Thanks for watching.